So in the last section I described the tagging problem and described how we essentially have a supervised learning problem where we have example tag sequences and we want to learn a model or function from those example tag sequences. In this next section of the lecture, I want to describe a method for deriving supervised learning algorithms called generative models. And as I said before, this is a very important kind of supervised learning model, and we'll see it come up time and time again in the course. So in supervised learning problems, we have the following setting. We're going to assume that we have a set of training examples, which I'll write as xi, yi for I equals 1 to m. And each xi is referred to as an input, whereas each yi is referred to as a label. So let's be specific. In the part of speech tagging example, we might have the following. x1 might be the following sentence. The dog laughs. And y1 would be the underlying tag sequence for that sentence. For example, determiner, noun, verb. We might have x2 is equal to the cat box, and y2 is equal to determiner, noun, verb again, and so on and so on. So in the part of speech tagging case, each training example consists of a sentence as the what's called the input, and an entire tag sequence as the associated label. And we might have a few hundred or a few thousand or maybe even a few tens of thousands of examples like this. So given these training examples in supervised learning problems, the task is to learn a function f that maps inputs x to labels f of x. So we want to, for example, in part of speech tagging again, learn a function that takes a sentence as input and maps it to a part of speech tag sequence as the output. So the first kind of model you might consider for supervised learning is what's called a conditional model. And that goes as follows. In a first step, in the learning step, we will actually learn a distribution, py given x, from the training examples. So we'll have some method that takes these training examples as input and returns a distribution, py given x, as the output. And in general, this distribution will have various parameters which are estimated from these training examples, a bit like the trigram parameters we saw in the first lectures on language modeling. Okay, so that's step one. We learn a conditional distribution py given x from the training examples. In a second step, for any test input x, we simply define f of x to be the y that maximizes this conditional probability. So in applying this model that we've learned, we take an input x as the input to the model, search through all the different possible labels y, and return the most likely y under this conditional model. Okay, so that's a conditional model. It's a very natural approach. It's probably one of the first things you would think of for these tasks, but as I'll show in a second, there is an alternative, so-called generative models. So in generative models, we again assume this scenario where we have training data, nothing changes here, and the task is again to learn a function that maps inputs x to labels f of x. And in generative models, we actually do something slightly different from what I showed you before, in that we're going to learn a joint distribution, pxy, over inputs x paired with labels y. So remember, on the previous slide, we had py given x. That's a conditional model. We're not going to do that. Instead, we're going to learn a joint model, px given y. Now, very often, this model takes the following form. We use Bayes' rule, or rather the rule of conditional probability, to factor this into two different terms. P of y This is often referred to as a prior. This can be thought of a measure of the prior likelihood of the label y, how likely y is a priori, and this is a sort of conditional generative model. So this is the conditional probability of x given y, the probability of generating x given that we have y. We'll see soon, and we'll see many times in this course, that it's very natural often to come up with models of this kind of form. So one interesting thing about these joint distributions is they're quite flexible. And they are, in some sense, more general than the discriminative model I showed you earlier. Let me just illustrate this through this important relationship. So given that I've learned a joint model, I can always calculate the conditional probability of any y given x using Bayes' rule as follows. So I have py times p of x given y. That's the form I've shown you here. I'm assuming that we're using this form. And on the denominator, I just have p of x. Like I said, this is just Bayes' rule, where p of x is derived as sum over y, p of y times p of x given y. Okay, so the important point here is that given a joint distribution, I can easily derive a conditional distribution. And in that sense, a joint distribution is a little bit more general than a conditional distribution. So there's actually a lot of back and forth between these two model types. This is often referred to as a discriminative model, or rather, I should be more precise, estimating py given x directly is often referred to as a discriminative model. And we will actually see a lot of discriminative models later in the course. P of x given y, sorry, P of x and y is often referred to as a generative model. And that is what we're going to see in this lecture. And there are pros and cons of these two model types. There's a lot of very interesting research in both of these areas and a lot of back and forth between these two model types. Okay, so that's a generative model. We learn this joint distribution. The important question, though, is how do we apply that to a new test example? And here's where we see something interesting. So, as before, we're going to take some input x, and we're going to define f of x as simply the y that maximizes the conditional probability of y given x. And I can substitute in here, using Bayes' rule, the form I showed you on the previous slide. I'm assuming here that I have a generative model. And an important characteristic of this equation is that p of x does not vary with y. So this denominator is actually constant with respect to y. So notice we're taking argmax over y. We're searching for the y that maximizes this entire term. Because this denominator is constant, if we're looking for the argmax, we can simply discard it and look for the y that maximizes the product of two terms, p of y and p of x given y. And that can be very convenient because from a computational point of view, calculating px can sometimes be rather painful. And so we don't actually need to do that when applying this type of model.